Serge Bolongi is a partner of our LDV Vision Summit since we started 10 years ago. He is also one of our LDV experts. Unfortunately, Serge could not be able to join us live today, so he has made a video to intro our next guest, and I will play that video now.
My name is Serge Bolongi. I'm a professor of computer science at the University of Copenhagen, and I'm the director of the Pioneer Center for Artificial Intelligence. It's really a pleasure to get to participate again in the latest LDV Vision Summit. Evan and I first collaborated on the LDV Vision Summit 10 years ago, back in New York City, when I had just moved there, and it's really been an amazing opportunity to get to participate every year since then in this outstanding event. Right now, I would like to introduce you to our next speaker, Anuroop from Meta. Anuroop is an AI researcher at Meta FAIR, applying deep learning to scientific problems. Over the last few years, his focus has been on using AI to discover materials for addressing climate change as part of the Open Catalyst and OpenDAC projects. He will share insights into recent innovations in machine learning aimed at discovering new materials for carbon capture.
Hi, I'm Anuroop. I'm going to talk about our work on OpenDAC, computational material discovery for carbon dioxide removal. As atmospheric carbon dioxide levels keep rising, the effects of climate change continue to become more severe, including more frequent forest fires, longer droughts, more intense storms, and so on. So there's an urgent need to reduce global carbon dioxide emissions. At Meta, we're interested in using AI to fight climate change and achieve net zero emissions. One of the most promising emerging technologies for decarbonization is called direct air capture, or DAC, which involves capturing carbon dioxide directly from ambient air. In a DAC system, we pass ambient air over a surface coated with a special material that is called a sorbent that attracts carbon dioxide. The carbon dioxide in the air sticks to this sorbent, and it can later be extracted and stored underground or converted into fuels. While DAC is promising, it needs to be scaled up by 5 to 6 orders of magnitude before we can reach net zero emissions. This requires reducing operating costs significantly. We can accomplish this by discovering better sorbent, that is, the materials that the carbon dioxide sticks to. So how do we find these sorbents? Well, one potential source of sorbents is a class of materials called metal organic frameworks, or MOFs. A few examples of these MOFs are shown in this slide. These are porous materials that have a very large surface area, and their chemistry can be tuned for specific applications, including DAC. Better sorbents can be found by searching through the space of all possible MOFs. The problem, however, is that the space of MOFs is extremely large, and we have to computationally model millions of them, or even billions of them, to find good sorbents. And the traditional methods for doing this kind of modeling often incur a trade-off between speed and accuracy. Quantum mechanical methods, which are very accurate, are also very slow, while classical force field methods are very fast, but they're not very accurate. Ideally, we would like to have a method that is both fast and accurate, and that is where machine learning comes into the picture. By training ML models to approximate quantum computations, we can get the best of both worlds. The OpenDAC project was conceived by our team in collaboration with Georgia Tech to develop such machine learning models. We created an open source dataset of 40 million quantum computations. Creating this dataset required over 400 million CPU hours of compute, which is well beyond the reach of most groups working in this space, but we were fortunate enough to have access to a large amount of idle hardware at Meta that we used to create this dataset. Next, we trained state-of-the-art graph neural networks based on the Equiformer V2 architecture that was developed by our team. This model is much more accurate than classical methods and also much faster than the quantum methods. Using this data set and this model, we were able to discover over 240 potential sorbents that were previously unknown. So what is next for DAC sorbent discovery? The methods I've described so far involve searching for good materials within a large database of known materials. So we are limited to previously known materials with these methods. We can do even better by leveraging recent advances in generative AI. Using Gen AI, we can directly generate materials with the properties we care about. This has the potential to discover completely novel materials much more quickly. We have recently developed two new generative models, one based on large language models and one based on Riemannian flow matching that we will employ to discover even better solvents in the future. So to conclude, AI can accelerate the process of discovering new materials for direct air capture from decades to months. We've already used these methods to discover hundreds of potential sorbents, and we have more to come in the next few months. You can check out our project at the URL listed here and in the QR code. Our dataset, models, code, the discovered promising materials are all available as open source there. Similar methods can also be used for many of the most pressing problems in the world today, like creating longer lasting batteries, synthesizing new fuels, designing new drugs, and so on. I envision a future where we can use AI to create custom materials and molecules for these use cases and more within days or weeks. The possibilities of AI in chemistry are really endless. Thank you.